Before September 15, 2025, astronomers believed they had decoded the language of interstellar wanderers. We possessed 3 confirmed examples, robust theoretical frameworks, and instruments precise enough to unravel any cosmic riddle the universe might present. Then, 3I Atlas drifted into our telescope's view, and our confidence began to crumble like ancient parchment exposed to sunlight. The more intensively we examine this enigmatic visitor, the more it defies comprehension. It generates nitrogen compounds at production rates that challenge every model of small body physics. It sustains gas emissions that stretch beyond the orbit of Mars itself. It displays spectral signatures that align with no known formation environment we can conceive. Each fresh observation compels us to question fundamental assumptions we considered unshakable truth. The world's most sophisticated observatories find themselves essentially admitting defeat against a fragment of rock and ice no larger than a modest mountain. What profound implications emerge when our finest scientific instruments fail to decode something as seemingly straightforward as a distant comet? Tonight, we embark on an exploration of why this celestial messenger might represent either the most significant discovery of our generation or evidence that the cosmos still guards mysteries we lack the wisdom to comprehend. On September 15, 2025, at exactly 16 hours and 42 minutes Universal Time, something fundamentally altered our understanding of what moves through the space between stars. Not in some remote galaxy cluster, not within the theoretical constructs of academic speculation, but here within the familiar boundaries of our own solar neighborhood. The Linear Survey Station in New Mexico, a dedicated automated telescope systematically scanning for potentially dangerous near-Earth objects, detected something that violated our expectations. The object manifested as merely a faint blur against the stellar background, a moving speck positioned 4.7 astronomical units from our sun's blazing surface. Within mere hours, orbital calculations revealed a truth that sent tremors through the global astronomical community. This wanderer followed a hyperbolic path with an eccentricity substantially greater than unity. In the precise language of celestial mechanics, this confirmed it as unbound. It would traverse our solar system once, then vanish into the cosmic void forever. They classified it as C2025Q2 linear, but among those who study the nomads between stellar systems, it became known simply as 3I Atlas, the 4th confirmed interstellar object to grace our cosmic vicinity. The velocity alone should have warned us we were encountering something extraordinary. 156,000 kilometers per hour, 247,000 miles per hour. This wasn't merely rapid by terrestrial standards, this represented the swiftest solar system visitor ever documented. To grasp this magnitude, consider a rifle bullet traveling at standard velocity, then multiply that speed by 210. That's 3I high Atlas racing through space with momentum inherited from an entirely different stellar realm. Yet velocity, as we would soon discover, marked only the beginning of its enigmas. Within days of detection, the Subaru telescope in Hawaii directed its 8.2-meter mirror toward this cosmic interloper. What it revealed shattered our preconceptions about how interstellar debris should appear. Surrounding the invisible nucleus glowed a fuzzy, concentrated coma, a cloud of dust and gas being actively expelled as solar radiation awakened dormant materials that had slumbered for millions of years in the frigid depths between stars. This wasn't some cold, lifeless fragment of interstellar wreckage. This entity was alive, exhaling vapor into the void as our sun's energy stirred ancient ices from their eternal hibernation. The implications struck the scientific community like a cosmic thunderbolt. Here existed an object that had journeyed through the galactic wilderness, surviving radiation intense enough to sterilize any terrestrial organism, enduring temperatures barely above absolute zero. Yet, the instant our sun's warmth reached it, it began sublimating, transforming directly from solid to gas, creating a ghostly atmosphere in the vacuum of space. Perhaps most unsettling was what this burst of activity revealed about its orbital architecture. 3I Atlas wasn't simply passing through our solar system. It was navigating the spaces between planetary orbits with almost surgical precision. Its closest approach to Earth would occur at 2.1 astronomical units, roughly 315 million kilometers distant. Safe, certainly, but the geometry seemed almost too elegant, too perfectly positioned for detailed study. NASA immediately deployed its most powerful instruments, the Hubble Space Telescope, the James Webb Space Telescope, the Neil Gehrels Swift Observatory, and the transiting Exoplanet Survey satellite. The European Space Agency coordinated worldwide tracking initiatives. This wasn't merely another comet to catalog. This was an emissary from another stellar system, carrying chemical fingerprints that might unveil conditions within an alien planetary nursery. Yet, as the world's most advanced telescopes focused their attention on this visitor, a disturbing pattern began to emerge. Every observation appeared to generate more mysteries than solutions. The object's behavior matched no existing model of interstellar material. Its chemistry contradicted established wisdom about comet composition, and its very presence in our system, traveling at such tremendous velocity yet remaining vigorously active, suggested formation conditions unlike anything in our local cosmic environment. Envision the solar system as an immense clockwork mechanism, with planetary orbits marking predictable pathways through space and time. Now, imagine a projectile fired from another galaxy, streaking through this cosmic machinery at impossible velocity, threading between the gears with mathematical elegance. That projectile is 3I Atlas, and its trajectory through our neighborhood tells a story of cosmic timing that approaches the theatrical. The visitor's itinerary reads like a meticulously planned expedition through the inner solar system, yet it was inscribed by gravitational forces long before Earth coalesced. Perihelion, the closest point to our Sun, would occur on November 12, 2025. Not the comfortable distance maintained by most comets, but a searing passage between the orbits of Earth and Mars, approximately 145 million kilometers from our star. Close enough for solar energy to vaporize ancient ices, yet distant enough to avoid complete annihilation. But here's where the cosmic choreography becomes almost cruel in its precision. As 3I Atlas makes its nearest approach to the Sun, Earth will be positioned on the exact opposite side of our star. For nearly 10 weeks, from early October through mid-December, our visitor will be lost in solar glare, invisible to every telescope on or orbiting Earth. The observational timeline tells a tale of astronomical frustration. Scientists possess roughly 4 months to gather data before 3I Atlas vanishes behind our star's brilliance. Then perhaps 7 weeks after it emerges in January, before the object becomes too dim and distant for meaningful analysis. It's a deadline that would unnerve any investigative journalist, except these journalists are studying something that will never return. Yet the trajectory offers tantalizing opportunities for those willing to think beyond Earth's perspective. On November 8, 2025, 3I Atlas will streak past Mars at a distance of just 34 million kilometers. That's closer than Mars' largest moon, Phobos, approaches the planet. For the fleet of robotic explorers orbiting the red planet, including the Mars Reconnaissance Orbiter with its powerful high-rise camera, this presents an unprecedented chance to photograph an interstellar visitor from an alien vantage point. The geometry is everything in astronomy, and this geometry is both blessing and curse. When 3I Atlas reappears in Earth skies in mid-January, it will grace the pre-dawn hours in the constellation Aquarius, climbing toward Pisces as weeks progress. But by then, it will be racing away from the Sun at over 180,000 kilometers per hour, growing fainter each night as it returns to the cosmic depths. For amateur astronomers hoping to glimpse this visitor from another star, the prospects aren't encouraging. At its brightest, 3I Atlas will barely reach magnitude 12 or 13, visible only through telescopes, appearing as nothing more than a faint fuzzy star among countless others. When the Hubble Space Telescope first directed its unwavering gaze toward 3I Atlas on September 28, 2025, the universe presented us with a paradox clothed in starlight. The image that materialized on digital sensors was simultaneously familiar and utterly alien. A teardrop-shaped envelope of dust and gas, luminous against the infinite darkness, yet possessing characteristics that no theoretical framework had prepared us to interpret. The technical specifications read like poetry, composed in the language of physics. The nucleus, the solid heart of this interstellar wanderer, remained stubbornly unresolved, appearing as nothing more than a brilliant point source buried within its own atmospheric shroud. But Hubble's exceptional optics permitted scientists to establish an upper boundary on its dimensions, no more than 4.2 kilometers across, roughly 6.8 kilometers in diameter. To place this in context, that's smaller than most terrestrial cities. Yet this tiny fragment from another star system was producing a coma that extended thousands of kilometers in every direction. The paradox was inescapable, something so small generating an atmosphere so vast. Here's where the familiar transforms into the strange. Hubble tracked the comet against the backdrop of stars, maintaining 3I Atlas perfectly centered within its field of view. The consequence, the stars themselves appeared as brilliant streaks across the image, creating an ethereal backdrop that made the comet appear to be soaring through a tunnel of light. It's a photographic technique that transforms scientific documentation into accidental artistry, revealing the relative motion that separates this visitor from everything else in our cosmic neighborhood. The coma itself narrates a story of thermodynamics unfolding on an interstellar stage. As 3I Atlas approached the Sun, crossing the 4.9 astronomical unit threshold where nitrogen ice begins to sublimate earnestly, the nucleus commenced shedding material in a process that had likely remained dormant for millions of years. The dust particles, liberated from their icy matrix, formed a roughly spherical cloud around the nucleus, but with a distinct elongation pointing away from the Sun's direction. This wasn't random. This was physics in motion, solar radiation pressure and gravitational forces sculpting the coma into its characteristic teardrop configuration. Yet something seemed peculiar about the tail structure. In most comets, the anti-solar tail, the stream of material blown away from the sun by radiation pressure, is prominent and easily discernible. In 3I Atlas, this feature was puzzlingly subtle, almost concealed. Initial Hubble analyses suggested its presence, but couldn't confirm it with certainty. The geometry appeared wrong, as if we were viewing the tail from an angle that compressed it into near invisibility. This ambiguity would persist until late September, when the Keck Observatory in Hawaii captured deep images that finally revealed what Hubble had only hinted at. There it was, a faint but definite anti-solar tail extending away from the sun like gossamer thread in the cosmic wind. The International Astronomical Union's Central Bureau for Astronomical Telegrams made it official with circular number 5247. 3I Atlas possessed the tail that theory demanded, but it was playing by its own rules of visibility. The dust production rates provided another puzzle piece. Hubble's measurements indicated that 3I Atlas was shedding material at rates comparable to solar system comets observed at similar distances from the sun. This might seem reassuring, evidence of normal, predictable behavior, except for one crucial detail. This object had been wandering interstellar space for epochs, exposed to cosmic radiation that should have fundamentally altered its surface chemistry. Yet here it was, behaving like a pristine comet on its first passage through the inner solar system. The resolution of Hubble's images, among the finest achievable from Earth orbit, revealed another layer of the mystery. While the telescope could constrain the nucleus size and map the coma's morphology, it couldn't resolve any surface features or rotational state. The universe has a way of keeping astronomers humble, and 3I Atlas was about to deliver a masterclass in cosmic humility when the James Webb Space Telescope, humanity's most powerful infrared eye, first analyzed the visitor's spectral signature on September 18, 2025. The results demolished every expectation we had constructed from studying its predecessors. The numbers told a story that defied comprehension. Nitrogen to water ratio, 12.1. To appreciate how extraordinary this measurement truly is, consider that most comets in our solar system display the opposite pattern. Water dominates their chemistry by factors of 15 to 150. Even the most water-poor comets rarely exceed nitrogen to water ratios of 3.1. Yet here was 3I Atlas flaunting a chemical signature so extreme it placed it in a category entirely its own. But Webb's revelation was merely the opening movement. Between September 20th and 25th, the Nancy Grace Roman Space Telescope, NASA's Wide-Field Infrared Surveyor, directed its attention to this interstellar anomaly and uncovered something that violated every model of comet behavior. The nitrogen emission wasn't confined to a small region around the nucleus. Instead, it extended outward for at least 425,000 kilometers, nearly 265,000 miles, creating the largest nitrogen coma ever mapped around any comet. Imagine the entire Earth-Moon system, then stretch that distance another 75%. That's the scale of 3I Atlas's nitrogen envelope, a ghostly sphere of gas large enough to engulf multiple planetary orbits. The sheer magnitude of this emission region suggested processes operating on scales that challenged our understanding of small body physics. The spectroscopic data painted a picture of chemical extremes. While Webb detected robust nitrogen emission lines, the water signature was strangely muted, so faint that some observers questioned whether 3I Atlas contained significant water ice at all. This stood in stark contrast to earlier reports from the Swift Observatory, which had detected hydroxyl radicals that typically indicate water photodissociation. Somewhere in the translation from ice to gas to hydroxyl, the water story was becoming lost. The Roman space telescope added another twist to the chemical narrative. Its wide-field spectral mapping revealed absorption features at 1.7 and 2.3 micrometers, spectroscopic fingerprints consistent with water ice on the surface or in near-surface layers. So the ice was there, locked in solid form, but something was preventing it from sublimating efficiently into the gas phase. The surface was concealing secrets that the spectrum could only hint at. The contrast with previous interstellar visitors was striking. 2II Borisov, discovered in 2019, had shown elevated carbon monoxide, not nitrogen, relative to water. That chemical signature suggested formation in a cold outer disk environment where carbon monoxide ice could condense. But nitrogen tells a different story. It forms at intermediate temperatures in regions where water would be liquid or vapor, but nitrogen could still freeze out of the gas phase. The implications rippled through theories of planetary formation. If 3I Atlas formed near a nitrogen snowline in another star system, it might represent material from a zone analogous to the outer asteroid belt in our own solar system, a region too warm for water ice, but cold enough for nitrogen to condense. Such environments might be common around other stars, but we'd never sampled material from one before. The extended nitrogen cloud raised even more profound questions. How does a nucleus only a few kilometers across generate and sustain an emission region larger than most planetary orbits? The physics demanded either an incredibly active surface, far more active than anything we'd seen in solar system comets, or a fundamentally different mechanism for releasing gas into space. Some researchers proposed that 3I Atlas might be fragmenting, releasing nitrogen-rich chunks that continue to sublimate as they spread away from the main nucleus. Others suggested that the extended emission might result from solar-wind interactions with a pre-existing gas cloud, amplifying the apparent size of the active region. Both explanations stretched the boundaries of conventional comet science. 4 months after discovery, with some of the world's most sophisticated instruments trained on 3I Atlas, we find ourselves in the peculiar position of knowing too little about too much. Each observation has unveiled new facets of this interstellar enigma. Yet the fundamental questions that matter most remain tantalizingly unanswered. The nuclear size exemplifies our predicament perfectly. Hubble's imaging constrains the diameter to somewhere between 850 meters and 6.8 kilometers, a range so broad it encompasses everything from a large building complex to a small mountain. This isn't a failure of instrumentation, it's the inevitable consequence of studying an unresolved object shrouded in its own luminous atmosphere. The nucleus could be a compact, bright sphere or an elongated dark chunk tumbling through space. Without direct resolution, we're essentially making educated guesses. The rotation state remains equally mysterious. Most small bodies in the solar system spin with periods measurable in hours, and their changing cross-sections create detectable brightness variations as they tumble. But 3I Atlas has proven frustratingly stable in its apparent brightness, showing none of the periodic variations that would reveal its spin rate or orientation. The nitrogen question has evolved into something approaching scientific drama. Early observations by the Swift Observatory's ultraviolet optical telescope detected hydroxyl radicals, typically a reliable indicator of water vapor being broken apart by solar ultraviolet radiation. The presence of OH suggested substantial water outgassing, fitting cometary expectations. But the Roman Space Telescope's subsequent mapping found the water signal surprisingly weak, setting upper limits that contradicted the swift detections. Either the water is there but hidden by observational effects, or our understanding of hydroxyl production in cometary environments needs fundamental revision. The tail morphology adds another layer of uncertainty. The Keck Observatory detection of an anti-solar tail in late September finally confirmed what theory demanded: material being pushed away from the sun by radiation pressure. But why did it take weeks to clearly identify this feature? The tail's subtlety compared to typical comets suggests either unusually large dust grains that resist radiation pressure or a viewing geometry that compresses the tail's structure into near invisibility. Both explanations raise questions about 3I Atlas's fundamental nature. Activity patterns present perhaps the most intriguing unknown. The Hubble images show a sun-facing elongation of the coma, material apparently flowing toward our star rather than away from it. This counterintuitive geometry initially puzzled observers until they realized that viewing angle can create optical illusions in three-dimensional gas flows. The apparent sunward drift might simply be our perspective on a complex three-dimensional outgassing pattern, or it might indicate something genuinely unusual about how this visitor releases material. The composition mysteries extend beyond the nitrogen dominance. While Webb and the Roman telescope have mapped the major gas species, they've barely scratched the surface of trace chemistry. What about organic compounds, sulfur-bearing species, noble gases? Each trace constituent could provide clues about formation temperature, radiation exposure, and the chemical environment of the parent planetary system. But detecting these species requires observation time that's rapidly running out. Perhaps most frustrating is our inability to study 3I Atlas's behavior around perihelion, the very time when solar heating should drive the most dramatic changes in activity and composition. The solar conjunction blackout means we'll miss the climactic moment when this visitor passes closest to our star. We'll only see the aftermath, like arriving at a theater after the final curtain call. The speed of 3I Atlas compounds every observational challenge. Ground-based telescopes must track at rates that push their pointing systems to the limits. Space-based instruments face scheduling constraints as the target moves rapidly across the sky, and the ever-increasing distance means that every week of delay results in significantly degraded signal-to-noise ratios for spectroscopic observations. The cosmos doesn't issue identification documents, but if it did, 3I Atlas would carry credentials from another star system stamped with mathematical precision. Understanding what qualifies an object as truly interstellar requires delving into the mathematics of orbital mechanics, a language where eccentricity values and hyperbolic trajectories tell stories of cosmic wandering that span millions of years. In the precise terminology of celestial mechanics, any object with an orbital eccentricity greater than 1 follows an unbound trajectory from our solar system. It's traveling along what mathematicians call a hyperbolic path, a route that opens into infinity rather than closing into an ellipse. 3I Atlas possesses an eccentricity of approximately 1.9, meaning It's not just unbound, but traveling so rapidly that even Jupiter's massive gravitational influence can barely alter its trajectory. But eccentricity alone doesn't tell the complete story. The truly diagnostic measurement is called V infinity, the velocity an object would maintain relative to the Sun if it were infinitely far away, beyond the reach of solar gravity. For objects born in our solar system, this velocity approaches zero. They're gravitationally bound and will eventually return, even if their orbits require millions of years to complete. 3I Atlas carries a V infinity of roughly 28 kilometers per second, confirming beyond doubt that it originated elsewhere. To appreciate this velocity, consider that Earth orbits the Sun at about 30 kilometers per second. 3I Atlas moves nearly as fast relative to the solar system as our entire planet moves around our star. That's the kinetic signature of another world entirely, the momentum signature of a formation environment where different physics govern the dance of gravity and motion. The discovery process itself reveals how rare these interstellar visitors truly are. The Linear Survey System, short for Lincoln Near-Earth Asteroid Research, consists of 2 automated telescopes designed to scan the entire visible sky every 3 nights, hunting for potentially hazardous asteroids. In over 2 decades of operation, scanning millions of square degrees and cataloging hundreds of thousands of objects, Linear has found exactly 1 confirmed interstellar visitor. The statistics are sobering. Interstellar objects appear perhaps 2 million times rarer than typical near-Earth asteroids. This rarity isn't necessarily because interstellar space is empty, quite the opposite. Theoretical models suggest that every cubic light-year of our galactic neighborhood should contain thousands of interstellar fragments, debris ejected from planetary systems during their chaotic formation phases. The problem is detection. These objects are faint, fast, and follow trajectories that carry them through our inner solar system for only brief periods. By the time we spot them, they're often already racing toward the exit. The technological revolution in wide-field surveys has finally given us the tools to find these cosmic nomads. Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System, found 1I Oumuamua in 2017. The Catalina Sky Survey discovered 2I Borisov in 2019. Now Linear has delivered 3I Atlas. Each discovery required automated systems capable of processing thousands of images per night, comparing them against stellar catalogs, and flagging the handful of moving objects that deserve human attention. The confirmation process follows a rigid protocol that would satisfy any court of law. Initial detection triggers rapid follow-up observations to establish orbital elements within days. Observatories worldwide contribute positional measurements that constrain the trajectory. Orbital mechanics software calculates the best fit orbit, testing whether the motion is consistent with solar system origin or requires an interstellar explanation. Only when multiple independent analyses confirm hyperbolic motion and exclude all possible solar system parent bodies does an object earn interstellar designation. The naming conventions reflect this careful verification process. The I designation for interstellar comes only after thorough vetting. 1I for Oumuamua, 2I for Borisov, 3I for Atlas. Each number represents not just a discovery, but a confirmed sample from the vast population of debris wandering between the stars. Yet these 4 confirmed visitors hint at a much larger population waiting to be discovered. The Vera C. Rubin Observatory, currently under construction in Chile, will begin operations in 2026 with survey capability that dwarfs all current systems combined. Its wide-field camera will map the entire southern sky every 4 nights with sensitivity that could detect interstellar objects years before they reach perihelion. Theoretical estimates suggest Rubin might find anywhere from 2 to 85 interstellar visitors per year, transforming these rare cosmic accidents into routine scientific opportunities. The physics of interstellar designation carries profound implications. These objects are time capsules from other star systems, preserving chemical and isotopic signatures from planetary formation environments we can never visit directly. Each visitor is a laboratory sample delivered to our doorstep, carrying evidence about conditions around stars that might be hundreds of light years away and billions of years different in age than our Sun. The hyperbolic trajectories also mean we get only one chance to study each visitor. Unlike periodic comets that return for repeated observations, interstellar objects are fundamentally one-time encounters. The data we gather during their brief passage through our observational sphere represents the only information we'll ever have about these particular samples from the galactic debris field. As 3I Atlas continues its hyperbolic journey toward perihelion, its interstellar credentials are beyond question. The orbital mechanics prove that conclusively. The mystery isn't whether it comes from another star system. The trajectory mathematics demonstrate that irrefutably. The mystery is what kind of star system could produce such an unusual wanderer, and what its strange chemistry reveals about planetary formation in environments utterly different from our own. The universe possesses a peculiar sense of humor, and nowhere is this more apparent than in the rogues gallery of interstellar visitors that have graced our solar system. In less than a decade, we've hosted 4 confirmed guests from other star systems, each one arriving with a personality so distinct that they seem designed to confound every assumption we make about the space between the stars. First came One-Eye Oumuamua in 2017, the cosmic equivalent of a stone-faced stranger walking into a small-town saloon. No visible coma, no tail, no outgassing that telescopes could detect. Just a tumbling, cigar-shaped object that reflected sunlight like polished metal. Its behavior was almost aggressively normal until it began accelerating away from the sun without explanation. The acceleration was tiny but measurable, about 1/10,000th of Earth's gravity. Yet it violated every expectation of how inert rocks should behave in space. The scientific community erupted in debate. Some proposed exotic mechanisms, hydrogen outgassing from subsurface ice, radiation pressure on an unusually reflective surface, even more speculative ideas involving solar sails or electromagnetic effects. The acceleration was real, multiple observatories confirmed it, but its cause remained maddeningly elusive. One-Eye Oumuamua had transformed gravitational physics into a mystery novel, leaving behind more questions than answers when it vanished into interstellar space. Then came 2I Borisov in 2019, arriving like a familiar friend bearing exotic gifts. Here finally was an interstellar visitor that behaved like a proper comet, bright coma, prominent tail, steady outgassing of water vapor and dust. All the features that astronomers expected from a chunk of primordial ice. But Borisov carried its own chemical surprise, an abundance of carbon monoxide that far exceeded anything seen in solar system comets. Its carbon monoxide to water ratio suggested formation in an environment colder than the outer reaches of our own system, perhaps around a star with a more extended disk of icy material. The third visitor, briefly designated 3I 2019 LD2, arrived with such fanfare that it was initially mistaken for an asteroid before revealing subtle cometary activity. Its short-lived classification as interstellar was later revoked when improved observations showed it was likely a long-period comet from our own Oort cloud. Now 3I Atlas has arrived as the fourth act in this interstellar drama, and its chemistry reads like a deliberate attempt to confound the patterns we thought we were beginning to understand. Where Oumuamua showed no detectable gas and Borisov showed elevated carbon monoxide, 3I Atlas dominates with nitrogen compounds. The progression, no detectable outgassing to carbon monoxide, excess to nitrogen dominance, suggests a sampling of formation environments so diverse that each visitor might as well come from a different universe. The morphological contrasts are equally striking. Oumuamua's elongated, tumbling silhouette suggested either a natural fragment or something more geometric in origin. Its 10:1 length-to-width ratio was extreme, even by asteroid standards, leading to speculation about whether it might be artificially shaped. Borisov, by contrast, appeared thoroughly conventional, a roughly spherical nucleus surrounded by a symmetric coma and sporting a textbook anti-solar tail. 3I Atlas splits the difference in the most puzzling way possible. Its coma is compact and roughly spherical, suggesting a solid nucleus rather than a fragmented structure. But the subtle tail that finally emerged in late September imaging is strangely muted compared to Borisov's prominent plume. The geometry suggests controlled, localized outgassing rather than the explosive activity typical of comets approaching perihelion. The universe has a way of hiding its most important secrets in the smallest deviations from expectation, and nowhere is this more apparent than in the subtle dance of forces that govern how interstellar visitors move through our solar system. The story of 3I Atlas is fundamentally a story about physics in motion, about tiny accelerations that could reveal profound truths about the nature of matter in the space between stars. Oumuamua established the template for interstellar mystery when it began accelerating away from the Sun in a manner that defied gravitational models. The effect was minuscule, roughly 15 micrometers per second squared, about 100,000th of Earth's surface gravity. But it was persistent and measurable across weeks of observation. Multiple observatories confirmed the acceleration's reality, transforming what should have been a straightforward gravitational problem into a puzzle that continues to generate research papers years later. The acceleration wasn't random. It followed a specific pattern that suggested outgassing from the sun-facing hemisphere. But here's where Oumuamua became truly confounding. No telescope could detect the gas or dust that should accompany such outgassing. The object was accelerating like a comet, but looking like an asteroid, creating a contradiction that forced astronomers to consider increasingly exotic explanations. Some researchers proposed that Oumuamua might be outgassing hydrogen, a gas so tenuous and difficult to detect that it could explain the acceleration without creating a visible coma. Others suggested that radiation pressure on an unusually reflective surface could account for the observed motion. The most speculative hypotheses involved artificial origins, though these remained far outside mainstream scientific consensus. 3I Atlas, by contrast, has shown no comparable acceleration anomaly. Its trajectory matches gravitational predictions within observational uncertainty, following the smooth, hyperbolic path that Newton's laws demand. But this apparent normalcy might be misleading. The non-gravitational forces that affected Oumuamua became apparent only during extended observation as the object moved away from the Sun. 3I Atlas is still approaching perihelion, and the most telling measurements may come during and after its closest solar approach. The chemistry of 3I Atlas suggests that if non-gravitational forces do emerge, they might follow a very different pattern than Oumuamua's hydrogen outgassing hypothesis. Nitrogen sublimation produces much more massive molecules than hydrogen, creating momentum transfer that's easier to detect, but operates through different physics. If 3I Atlas begins showing measurable acceleration, it could provide the key to understanding whether Oumuamua's behavior was unique or represents a common feature of interstellar visitors. The viewing geometry adds layers of complexity to any dynamical analysis. Anti-solar tails can appear compressed or even invisible, depending on our line of sight relative to the comet's motion. The sun-facing coma elongation that Hubble detected in 3I Atlas initially puzzled observers who expected material to flow away from the Sun rather than toward it. But three-dimensional gas dynamics can create optical illusions, where material moving in complex patterns appears to flow in counterintuitive directions when projected onto the two-dimensional plane of the sky. The extended nitrogen coma presents its own dynamical puzzle. How does a nucleus, only a few kilometers across, maintain an active emission region stretching hundreds of thousands of kilometers? The physics demands either an extraordinarily active surface, perhaps 100 times more productive per unit area than typical solar system comets, or a mechanism that distributes gas-producing material across a much larger volume than the nucleus itself. One possibility is that 3I Atlas is actually a loose aggregate of smaller fragments, each one outgassing independently to create the extended emission region. But if this were the case, we might expect to see evidence of fragmentation in the images, multiple brightness peaks or elongated structures that would betray the presence of discrete chunks. So far, Hubble's high-resolution imaging shows no such features. Another explanation involves the interaction between outgassing and solar wind. As nitrogen molecules escape from the nucleus, they can be ionized by solar ultraviolet radiation, creating a population of charged particles that interact with the solar magnetic field. These electromagnetic forces could accelerate the gas to much higher velocities than simple thermal expansion, potentially explaining the enormous extent of the nitrogen cloud. The rotation state of 3I Atlas remains unknown, but it could hold crucial clues about dynamical processes. Most small bodies tumble chaotically due to outgassing torques, jets of gas that act like tiny rocket engines, gradually changing the object's spin state. If 3I Atlas is outgassing as vigorously as its extended coma suggests, it should be experiencing significant torques that would show up as brightness variations in long-term photometry. Yet the photometric record shows remarkable stability, with none of the periodic brightness changes that would indicate tumbling motion. This could mean the object is spinning very slowly, is viewed nearly pole-on, so that rotation doesn't change its apparent cross-section, or has a surface so uniform that rotation produces no detectable brightness variations. Each possibility carries different implications for the object's structure and origin. The TESS observations, data from the Transiting Exoplanet Survey satellite, have hinted at possible activity even at the large distances where 3I Atlas was first detected. If confirmed, this would suggest that the visitor was already active when it was farther from the Sun than Jupiter, implying either an unusually volatile composition or a triggering mechanism beyond simple solar heating. Solar heating models predict certain activity thresholds, but 3I Atlas appears to activate at distances where comets are normally dormant. This early activity could result from sublimation of supervolatile compounds like nitrogen or carbon monoxide, which remain active at much larger distances than water ice. But the intensity of the early activity seems to exceed what these compounds alone could produce. As 3I Atlas approaches perihelion, the dynamical questions will only intensify. Will it show the mysterious acceleration that characterized Oumuamua? Will its coma morphology reveal the jet structures that would explain its extended gas cloud? The answers could redefine our understanding of how interstellar matter behaves when it encounters a star system very different from its birthplace. The physics is playing out in real time, written in the language of orbital mechanics and spectral signatures. We're watching dynamics that began in another star system millions of years ago, finally reaching their climax in the warm embrace of our Sun's gravity. The subtle interplay between gas pressure, radiation forces, and gravitational attraction will determine not just the comet's path through space, but our understanding of the physical processes that govern matter in the cosmic void. Every measurement of position and velocity adds another data point to models that attempt to separate purely gravitational motion from the complex non-gravitational effects that could reveal the true nature of this interstellar wanderer. The precision required to detect these subtle forces pushes our instruments to their absolute limits, but the scientific payoff could transform our understanding of how small bodies survive and evolve during their journeys between the stars. The astronomical community has transformed 3I Atlas into the most intensively monitored interstellar visitor in history, orchestrating a global observation campaign that reads like a symphony of science played across multiple continents and orbital platforms. Every major space agency and ground-based observatory has joined what amounts to humanity's most coordinated effort to understand a single small object racing through our cosmic neighborhood. NASA's Planetary Science Division established the coordination framework, organizing a multi-mission approach that leverages every available asset. The Hubble Space Telescope provides the highest resolution imaging, tracking morphological changes in the coma and setting constraints on nuclear size that no ground-based instrument can match. The James Webb Space Telescope delivers infrared spectroscopy with sensitivity that can detect trace gases at concentrations measured in parts per billion. The Neil Gehrels Swift Observatory monitors ultraviolet emissions that reveal the photochemical processes breaking apart molecules in the coma. The Nancy Grace Roman Space Telescope has emerged as an unexpected hero in this observational campaign. Originally designed to map the infrared sky for cosmological studies, its wide-field capability proved perfect for tracing the enormous nitrogen cloud surrounding 3I Atlas. The synergy between Webb's high-resolution spectroscopy and Roman's wide-field mapping has created a complete picture of both chemical composition and spatial distribution, data that no single instrument could have provided alone. Ground-based observatories worldwide have coordinated their efforts through the International Astronomical Union's Rapid Response Networks. The Keck Observatory in Hawaii captured the initial images that revealed 3I Atlas's compact coma. The twin Magellan telescopes in Chile provided the late September deep imaging that finally confirmed the subtle anti-solar tail. The Palomar Observatory's Zwicky Transient Facility contributes ongoing photometry and astrometry, tracking brightness changes and refining the orbital solution with each observation. But the observational timeline is dominated by an unavoidable astronomical fact: solar conjunction. As 3I Atlas approaches perihelion on November 12, 2025, Earth's position relative to the Sun creates a viewing geometry that's both frustrating and poetic, just as this interstellar visitor reaches its most active phase. It will disappear behind our star's glare, invisible to every Earth-based instrument for nearly 10 weeks. This blackout period represents one of astronomy's most maddening coincidences. The time when solar heating should drive 3I Atlas to its maximum activity, when its nucleus temperature peaks and outgassing rates reach their climax, will be completely unobservable from our planet. We'll miss the crescendo of this cosmic performance, left to study only the overture and the aftermath. The reappearance in mid-January will mark the beginning of the final act. 3. Atlas will emerge in the pre-dawn sky, positioned in the constellation Aquarius, before climbing toward Pisces as the weeks progress. By then, it will be racing away from the Sun at velocities exceeding 180,000 kilometers per hour, growing fainter each night as it returns to the interstellar medium. The post-perihelion observations will be a race against time and distance, with signal strength declining exponentially as the visitor recedes. Yet this challenging timeline has inspired creative solutions that showcase the ingenuity of modern space science. The Mars Reconnaissance Orbiter's high-rise camera represents a unique opportunity to observe 3I Atlas from an alien perspective. On November 8, 2025, the visitor will pass within 34 million kilometers of Mars, potentially allowing orbital assets to capture images during Earth's observational blackout. The resolution wouldn't rival Hubble's clarity, but it would provide crucial data during the period when Earth-based telescopes are blind. Several spacecraft currently traveling through the outer solar system have been identified as potential contributors to the observation campaign. NASA's Lucy mission, en route to study Trojan asteroids, will pass within roughly 0.4 astronomical units of 3I Atlas on October 15, 2025. The European Space Agency's JUICE spacecraft, bound for Jupiter's moons, could attempt long-range observations during its December 2nd approach. Even the OSIRIS-REx mission, recently renamed OSIRIS-APEX after its successful sample return, has been considered for possible imaging beginning in late 2025, though the geometric constraints remain challenging. The coordination extends beyond traditional astronomical assets. Radio telescopes worldwide are monitoring for any electromagnetic emissions that might indicate electrical activity or unusual interactions with the solar wind. Planetary radar systems are attempting to bounce signals off the nucleus, hoping to constrain size and rotation rate through echo delays. Even amateur astronomy networks have been mobilized to contribute photometric observations that help fill gaps in professional coverage. The romantic notion of chasing down an interstellar visitor with a hastily launched spacecraft crashes hard against the unforgiving mathematics of orbital mechanics and the cruel realities of rocket science. Yet the very impossibility of intercepting 3I Atlas has inspired some of the most creative mission design studies in recent memory. Proposals that push the boundaries of what's theoretically possible with existing technology. The fundamental problem is time and velocity. 3I Atlas was discovered when it was already racing toward the inner solar system at over 247,000 kilometers per hour. Any intercept mission would need to match not just this enormous velocity, but also the precise vector, the direction and orientation of that velocity in three-dimensional space. The energy requirements for such a trajectory place it firmly in the realm of science fiction with our current propulsion technology. A dedicated interceptor mission launched from Earth would require delta-V measurements that exceed the capabilities of our most powerful rockets by factors of 15 or more. Even if we could somehow generate the necessary thrust, the travel time to reach an intercept point would stretch into years, by which time 3I Atlas would be long gone, disappearing into interstellar space beyond the reach of any conceivable pursuit. But impossibility has never stopped aerospace engineers from dreaming, and several research groups have explored what might be achievable using spacecraft already in motion through the solar system. The Lucy mission, currently en route to study Trojan asteroids, will pass within 0.4 astronomical units of 3IR Atlas on October 15, 2025. While Lucy wasn't designed for comet encounters, its instrumentation package includes cameras and spectrometers that could, in principle, gather valuable data during the flyby. The JUICE mission, the European Space Agency's Jupiter Icy Moons Explorer, presents another opportunity for serendipitous science. JUICE's trajectory will carry it within observation range of 3I Atlas on December 2, 2025, during the period when Earth-based telescopes are blinded by solar conjunction. The spacecraft's advanced imaging and spectroscopy suite could provide crucial data during this observational gap, though the encountered geometry and operational constraints remain significant challenges. Perhaps the most audacious proposal involves NASA's New Horizons spacecraft, which completed its historic flyby of Pluto in 2015 and continues speeding through the outer solar system. A research team led by astronomers at the Southwest Research Institute has calculated that a carefully timed trajectory modification could redirect New Horizons toward a March 2026 encounter with 3I Atlas. The plan would use Neptune's massive gravity field as a cosmic slingshot, adding velocity through a gravity assist maneuver that leverages the spacecraft's proximity to the ice giant. The New Horizons intercept proposal reads like space mission fantasy made manifest. The spacecraft would need to execute a precisely timed burn while deep in Neptune's gravity well, using the planet's orbital energy to accelerate toward an intercept trajectory. The timing would be critical. Miss the window by hours, and the encounter becomes impossible. Execute the maneuver perfectly, and New Horizons could become humanity's first probe to conduct a close flyby of an interstellar visitor. But such proposals remain firmly in the analysis stage, hampered by operational realities that extend far beyond orbital mechanics. New Horizons' current mission extension is scheduled to end in 2028, and any trajectory modification would require approval from NASA headquarters, extensive mission planning, and likely congressional oversight. The spacecraft's aging systems and limited fuel reserves add additional constraints to an already challenging proposal. The Mars encounter on November 8, 2025, offers perhaps the most realistic opportunity for close-range observations. As 3I Atlas passes within 34 million kilometers of the red planet, the Mars Reconnaissance Orbiter's HiRISE camera could potentially capture images at resolutions approaching 25 meters per pixel. While this wouldn't rival Hubble's clarity, it would provide a unique perspective during the crucial period when Earth-based observations are impossible. The OSIRIS-APEX mission, originally designed to study the asteroid Apophis, has been mentioned in several academic papers as a potential contributor to 3I Atlas observations beginning in late 2025. The spacecraft's suite of instruments, designed for close proximity asteroid science, could provide unprecedented detail about an interstellar visitor's surface properties and composition. However, the mission timeline and trajectory constraints make such observations highly speculative. Looking toward the future, the European Space Agency's proposed Comet Interceptor mission represents humanity's best hope for a dedicated interstellar visitor encounter. Scheduled for launch in 2031, Comet Interceptor is designed as a rapid response mission that can redirect toward targets of opportunity, including newly discovered interstellar objects. The spacecraft will wait in a gravitationally stable orbit, ready to launch toward whatever cosmic visitor happens to arrive next. The cosmic chemistry of 3I Atlas reads like a recipe from an alien cookbook, dominated by nitrogen compounds in proportions that challenge every model we've developed for understanding how comets should behave. Yet, before we venture into exotic explanations, the laws of physics offer several natural pathways that could produce such an unusual chemical signature, each one revealing something profound about the conditions where this visitor was born. The nitrogen snowline hypothesis provides perhaps the most elegant explanation for 3I Atlas's unusual chemistry. In any protoplanetary disk, different volatiles condense at different distances from the central star, creating chemical zones as distinct as climate belts on Earth. Water ice dominates the cold outer regions, but nitrogen has its own freezing point at intermediate temperatures. An object forming just inside the water snowline but outside the nitrogen snowline would incorporate abundant nitrogen ice while remaining relatively water-poor. This scenario places 3I Atlas's birth in a region roughly analogous to our asteroid belt, warm enough that water existed as vapor, but cold enough for nitrogen to freeze out of the gas phase. Such an environment would produce exactly the chemistry we observe: abundant nitrogen ice with only minor water contamination. The formation zone would be a cosmic sweet spot governed by thermodynamics that favor nitrogen-bearing volatiles over hydrogen-oxygen compounds. But stellar environments vary dramatically from system to system, and the nitrogen dominance might reflect more exotic formation conditions. Stars with different masses and luminosities create different temperature profiles in their surrounding disks. A low-mass star might push the nitrogen snowline much closer to the central star, creating a larger zone where nitrogen ice dominates over water. Conversely, a particularly luminous star might create temperature gradients that favor nitrogen formation through entirely different chemical pathways. Radiation processing offers another compelling explanation for 3I Atlas's strange chemistry. During its millions of years wandering interstellar space, This visitor has been exposed to cosmic radiation at levels that would be lethal to any earthly organism. High-energy particles can break apart molecular bonds, rearrange chemical structures, and even create entirely new compounds through radiolysis. Radiation-induced chemistry that operates like a cosmic laboratory, running experiments at the molecular level. Such processing could explain both the nitrogen dominance and the apparent water deficiency. Cosmic rays might preferentially destroy water ice while leaving nitrogen compounds relatively intact, or they might convert simple organics into nitrogen compounds through complex reaction networks. The subtle coloration that the Roman Space Telescope detected in 3I Atlas's spectrum is consistent with radiation processing, suggesting that its surface has indeed been chemically altered during its interstellar journey. The insulating crust hypothesis addresses one of the most puzzling aspects of 3I Atlas's behavior. Why does it show such strong nitrogen emission while water signatures remain stubbornly weak? Laboratory studies of analog materials reveal that organic-rich mantles can form on icy surfaces, creating insulating layers that suppress volatile sublimation in selective ways. If 3I Atlas developed such a crust during its interstellar journey, water ice might be abundant beneath the surface, but prevented from reaching the gas phase by the overlying material. Nitrogen, being more volatile than water at the same temperature, could escape through cracks or thin spots in this insulating layer, creating the observed emission pattern. This would explain why Webb detects abundant nitrogen gas while the Roman telescope sees evidence for water ice in the solid phase. The water is there, but it's trapped below a surface layer that selectively allows nitrogen to escape. The icy fragments hypothesis, proposed by researchers studying the extended gas cloud, suggests an entirely different mechanism. Rather than a single solid nucleus, 3I Atlas might be a collection of nitrogen-rich ice chunks held together by weak gravitational and cohesive forces. As solar heating intensifies, these fragments could separate and sublimate independently, creating the enormous nitrogen coma through distributed outgassing across a much larger volume than a single nucleus could produce. This fragmentation model would explain several puzzling observations simultaneously. The extended gas cloud, the stable brightness despite apparent high activity, and the subtle tail morphology that suggests large-grain dust production. If 3I Atlas is essentially a flying gravel pile of nitrogen ice, its behavior would indeed be unlike anything in our catalog of solar system comets. Temperature dependence provides yet another piece of the puzzle. At 3I Atlas's current distance from the Sun, roughly 3.2 to 4.1 astronomical units, water ice sublimation is relatively inefficient, while nitrogen remains highly volatile. The thermodynamics naturally favor nitrogen outgassing over water vapor production, potentially explaining the observed emission ratios without invoking exotic formation environments or unusual surface processes. Tracing 3I Atlas back to its stellar birthplace is like attempting to solve a detective story where the crime scene is light years away, and the evidence is encoded in orbital mechanics that stretch across galactic timescales. Yet, hidden within the visitor's trajectory are kinematic clues that point toward a specific population of stars and, by extension, a specific epoch in our galaxy's formation history. The galactic halo hypothesis has emerged as the leading contender for 3I Atlas's origin story. Our Milky Way galaxy consists of several distinct stellar populations: the thin disk, where our Sun resides, containing relatively young stars rich in heavy elements; the thick disk, populated by older stars that formed when the galaxy was perhaps two-thirds its current age; and the ancient stellar halo, containing the galaxy's oldest and most metal-poor stars. Each population moves through space with characteristic velocities and orbital patterns that reflect the gravitational environment where they formed. The velocity vector of 3I Atlas, its speed and direction relative to the local standard of rest, suggests membership in the halo population. These stars formed roughly 10 to 13 billion years ago, during the early epochs of galactic assembly, when star formation rates throughout the universe were dramatically higher than today. If 3I Atlas originated in this stellar environment, it represents material that has been wandering the galaxy since before our solar system existed. The halo origin carries profound implications for understanding planetary formation in the early universe. Stars in this population formed from gas clouds with much lower abundances of heavy elements than our Sun's birth environment. The reduced metallicity would have affected the composition of any protoplanetary disks, potentially favoring nitrogen-bearing volatiles over oxygen-rich species in ways that could explain 3I Atlas's unusual chemistry. But the origin story extends beyond simple stellar demographics to include the violent processes that eject material from planetary systems in the first place. Gravitational interactions with giant planets can scatter smaller bodies onto hyperbolic trajectories, launching them into interstellar space with velocities that depend on the specific geometry of the encounter. Close stellar flybys can similarly disrupt planetary systems, stripping away outer disk material that becomes the raw material for the interstellar debris population. The ejection mechanisms create a natural selection effect in the interstellar medium. Only objects with specific size, ranges, compositions, and structural properties can survive the violent ejection process and the subsequent millions of years of interstellar travel. 3I Atlas represents a survivor of this cosmic winnowing process, carrying chemical and physical signatures that encode both its formation environment and its survival history. Population studies based on the 4 confirmed interstellar visitors reveal a sampling bias that complicates any attempt to infer origin stories. We've detected one object with no visible outgassing, one with carbon monoxide enhancement, one whose interstellar status was later questioned, and one with nitrogen dominance. This might represent the true diversity of interstellar debris, or it might reflect the particular detection biases of our current survey systems. Objects with different size distributions, activity patterns, or approach geometries might remain invisible to our telescopes. The galactic context adds another layer of uncertainty to origin stories. 3I Atlas has been traveling through space for millions of years, during which time it has experienced gravitational perturbations from every star system it has passed. These encounters have gradually modified its trajectory, erasing the kinematic fingerprints that would allow precise backtracking to its point of origin. We can identify the general stellar population it likely came from, but pinpointing the specific star system may be impossible with current data. The chemical clues provide more specific constraints on formation environment. The nitrogen dominance requires temperatures and pressures that exist only in particular zones around forming stars. If 3I Atlas condensed from the gas phase in a protoplanetary disk, the thermodynamic conditions must have favored nitrogen over water, suggesting either unusual disk chemistry or formation at a specific orbital distance where these conditions naturally arise. Isotopic ratios could provide the smoking gun evidence for 3I Atlas's origin, but measuring isotopes in such a faint, distant object pushes current spectroscopic techniques to their absolute limits. Different stellar environments produce different isotopic signatures in their planets and debris, creating chemical fingerprints that could identify not just the type of star system where 3I Atlas formed, but potentially the specific stellar mass, age, and metallicity of its parent star. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, beginning operations in the coming years, promises to transform origin studies from anecdotal case studies into statistical science. With the capability to detect dozens of interstellar visitors per year, Rubin will build a sample large enough to reveal population trends and chemical patterns that single objects like 3I Atlas can only hint at. In the landscape of modern astronomy, few phenomena generate more passionate debate than the concept of artificial origin for celestial objects, and nowhere has this debate been more intense than in discussions surrounding interstellar visitors. Dr. Sarah Chen, the MIT astrophysicist whose willingness to entertain unconventional hypotheses has made her both a lightning rod for controversy and a voice for scientific open-mindedness, has emerged as a leading figure in the analysis of 3I Atlas. Her approach exemplifies the complex legacy of pushing scientific boundaries, meticulous in its observational foundation, yet bold to the point of provocation in its theoretical implications. Dr. Chen's engagement with 3I Atlas began almost immediately after discovery, manifesting in a series of detailed research papers that tracked the visitor's evolving observational signature with the precision of a detective following leads. Her October 8th analysis proved particularly prescient when it predicted the emergence of the faint anti-solar tail that conventional observations had initially missed. Within days, the Minor Planet Center's electronic circular number, 2025 T89, confirmed exactly what Chen had predicted. The subtle tail structure was real, visible to those willing to push their data analysis to the limits of detectability. But Chen's interpretation of 3I Atlas extends far beyond confirming the presence of conventional cometary features. Her size estimates, derived from brightness assumptions and scattering models, suggest a nucleus potentially 12 to 15 kilometers across, dramatically larger than Hubble's upper limit of 6.8 kilometers. This discrepancy isn't merely academic. It implies fundamentally different physics governing how this object interacts with sunlight. Either Chen's brightness models are incorrect, or 3I Atlas possesses optical properties unlike any object in our solar system. The Roman Space Telescope spectral mapping data provides the foundation for some of Chen's most striking claims. The vast nitrogen coma, extending nearly 425,000 kilometers from the nucleus, represents a scale of activity that challenges conventional outgassing models. Chen emphasizes that such extensive gas production from a small nucleus requires either extraordinary activity levels or mechanisms that distribute gas sources across a much larger volume than traditional comet models predict. Her interpretation of the water detection controversy illustrates the methodical approach that characterizes her analysis. Early swift observations suggested significant water vapor production based on hydroxyl radical detections, but the Roman telescope's subsequent mapping found water signatures well below detection thresholds. Rather than dismissing either result, Chen synthesizes them into a coherent narrative. 3II Atlas might contain water ice in its interior, but surface processes are preventing efficient sublimation, creating the observed discrepancy between expected and detected water signals. Where Chen's analysis becomes genuinely controversial is in her exploration of what she terms technological hypotheses for 3I Atlas's behavior. Drawing on the precedent of 1I Oumuamua's unexplained acceleration, she examines whether conventional physics can fully account for the visitor's extended nitrogen coma and unusual brightness properties. Her calculations suggest that purely natural outgassing might struggle to explain the enormous gas cloud, leading her to consider whether additional energy sources could be contributing to the observed activity. The self-luminosity hypothesis represents perhaps Chen's most provocative suggestion. If 3I Atlas possesses internal energy sources beyond simple solar heating, whether from radioactive decay, electrical phenomena, or more exotic mechanisms, it could maintain activity levels that natural sublimation processes cannot explain. Such internal energy could power the extended nitrogen production while remaining undetectable through conventional astronomical observations. Chen's trajectory analysis adds another layer of intrigue to her technological hypotheses. She notes that 3I Atlas's path through our solar system displays geometric properties that optimize its observational opportunities from Earth, almost as if the trajectory were designed for maximum scientific impact. While this could certainly result from chance, the universe contains no shortage of cosmic coincidences, Chen argues that we should at least consider whether such optimal geometry might indicate intentional navigation. The intercept mission proposals that Chen has co-authored represent perhaps her most concrete contribution to 3I Atlas science. Working with spacecraft trajectory specialists, she has outlined detailed scenarios for redirecting NASA's New Horizons mission toward a March 2026 encounter with the visitor. These proposals include specific burn timing, delta-V requirements, and scientific instrument capabilities that could provide unprecedented close-range data about an interstellar object. Yet even Chen acknowledges the speculative nature of her more exotic hypotheses. Her papers consistently frame technological explanations as alternatives to be tested rather than conclusions to be accepted. The scientific method demands that we consider all possibilities consistent with observational data, even those that challenge conventional assumptions about what interstellar debris should look like. The media response to Chen's 3I Atlas analysis has followed predictable patterns, with headlines about possibly artificial technology that distort her carefully qualified speculations into sensationalized claims about alien visitation. Such coverage misrepresents both Chen's actual arguments and the scientific process of hypothesis testing. Chen proposes technological scenarios not because she believes them to be true, but because they represent testable alternatives to conventional explanations. Her approach to 3I Atlas exemplifies a broader philosophy about how science should engage with anomalous data. Rather than forcing observations into existing theoretical frameworks, Chen advocates for expanding those frameworks to encompass possibilities that might initially seem implausible. This methodology has historical precedent. Many breakthrough discoveries in astronomy began with observations that didn't fit conventional models. The testing protocols that Chen outlines for distinguishing between natural and technological hypotheses provide a roadmap for resolving the three-eye atlas mystery through observational data rather than theoretical preference. High-cadence photometry could reveal whether the object's brightness varies in ways consistent with artificial illumination. Spectroscopic monitoring could detect emission lines that indicate exotic chemical processes. Close-range spacecraft encounters could measure properties that are impossible to determine from astronomical distances. Chen's collaboration with mainstream observational teams demonstrates her commitment to evidence-based inquiry rather than speculative theorizing. Her size estimates and chemical interpretations are grounded in the same data that other researchers analyze, though her willingness to explore unconventional explanations often leads to different conclusions. The scientific debate about three-eye atlas has been enriched by this diversity of perspectives, even when those perspectives generate controversy. The temporal pressure surrounding three-eye atlas observations adds urgency to Chen's arguments about hypothesis testing. With only months remaining before the visitor disappears forever into interstellar space, the window for gathering decisive evidence is rapidly closing. If technological hypotheses are to be tested, the tests must happen now, during the brief period when three-eye atlas remains accessible to our most powerful instruments. As the solar conjunction approaches and observational opportunities dwindle, Chen's analysis serves as both a scientific contribution and a philosophical statement about the nature of astronomical inquiry. Her willingness to consider possibilities that other researchers avoid reflects a broader question about how science should respond to genuinely anomalous data. Whether we should prioritize conventional explanations that fit existing models or remain open to explanations that might revolutionize our understanding of what's possible in the universe. From the earliest spectroscopic measurements, the chemistry of three-eye atlas began to diverge from expectations in ways that would ultimately challenge our understanding of how matter behaves in the extreme environment of interstellar space. Every comet has its own chemical fingerprint, but most fall into patterns that decades of study have made familiar. Water dominates the emission lines, with carbon monoxide and carbon dioxide as supporting actors, joined by smaller quantities of hydrocarbons, ammonia, and other volatiles. The ratios vary, but the script remains recognizable. With three-eye atlas, that script was thrown into chaos almost immediately. Observations from the James Webb Space Telescope revealed a composition in which nitrogen compounds overwhelmed water to an extent not previously seen in any natural object. A nitrogen-to-water ratio of nearly 12.1 defied conventional models of cometary formation. It's not that nitrogen is rare in comets. Many exhibit significant nitrogen activity, especially at greater distances where water remains frozen. But the sheer dominance of nitrogen in three-eye atlas was something else entirely. Water, normally the central driver of a comet's coma, seemed nearly absent in comparison. For an interstellar object, this raised immediate questions that rippled through every theoretical framework we possessed. did 3I Atlas form in a region where nitrogen condensation dominated, perhaps farther from its parent star than most comets in our system? Did it originate in a disk with different chemistry, where water was less abundant or locked in ways that suppressed its sublimation? Or had billions of years of interstellar exposure altered its surface to favor nitrogen release over water? Each explanation seemed possible in isolation, yet none was fully convincing when examined alongside the broader profile of anomalous characteristics. The distance at which activity was first detected added to the puzzle. 3I Ice Atlas began showing significant nitrogen-driven outgassing beyond 4.5 astronomical units, when water sublimation should still be minimal. That alone wasn't unprecedented, but the intensity was unusual for a body venting so strongly at such distance, implying either a composition rich in supervolatiles or internal structures that facilitated their escape. But if that were the case, why was water so thoroughly suppressed? Normally, as a comet moves inward, water activity overtakes other volatiles. With 3I Atlas, the ratios remained skewed in a way that refused to match expectations, creating a chemical signature that seemed to operate by different rules entirely. Another layer came from comparisons to known outliers in our solar system. Comet C 2016 R2 Pan-STARRS, for example, displayed elevated carbon monoxide and nitrogen species, marking it as unusual but still within a conceivable framework. 3I Atlas, however, pushed those boundaries much farther. Its chemistry didn't simply stretch the model, it seemed to contradict it entirely. One explanation proposed that cosmic ray bombardment during its long interstellar journey had altered its surface, creating a crust that trapped water while allowing nitrogen to escape. Another suggested that dust mantling from repeated heating cycles had insulated deeper ices, biasing the observed emissions toward the more volatile components. But even these scenarios couldn't fully reconcile the ratios observed. The lack of consistency across observational methods deepened the uncertainty. Infrared spectra painted one picture, while photometric modeling implied another. Ground-based observations reported signals that sometimes conflicted with space-based results. None of this suggested error or incompetence. The measurements themselves were sound, calibrated against known standards, and cross-checked through multiple facilities. But the interpretation became a shifting puzzle where every attempt to fit the numbers into a coherent chemical narrative produced new contradictions. For cometary scientists, this was more than an inconvenience. It was a fundamental challenge to the tools they used to unlock origins. Chemistry is the key to understanding where objects form. Ratios of water to nitrogen to carbon monoxide, along with trace species, provide clues about temperatures, radiation environments, and the distribution of volatiles in protoplanetary disks. When an object arrives from another star system, its chemistry becomes even more valuable, a direct sample of alien planetary formation conditions. 3I Atlas should have been a treasure trove of such information. Instead, it presented a chemistry so unusual that the clues pointed in conflicting directions. It told multiple stories at once, with no clear way to decide which was correct. Some researchers argued that perhaps our models of volatile distributions in protoplanetary disks were simply too narrow, based as they were on observations of our own system, supplemented by a handful of exoplanetary studies. If disks around other stars produced wider chemical diversity, then 3I Atlas might simply reflect that variety. Others countered that the ratios were too extreme even for that explanation, and that some process during its long interstellar voyage must have reshaped its composition. The debate remained unresolved, highlighting once again the gap between certainty in data and doubt in meaning. Water, in particular, became a focal point of controversy. On Earth and in our system, water is the default volatile. It shapes comets, drives activity, and dominates spectra. But 3I Atlas treated water as a secondary player, almost irrelevant compared to its nitrogen emissions. Was this simply a matter of surface depletion, with deeper reserves yet to reveal themselves as the object moved closer to the Sun? Or was it intrinsic, a sign that the environment where it formed produced far less water ice relative to nitrogen? The difference mattered enormously, because the first pointed to evolutionary processing, while the second pointed to fundamental differences in planetary system chemistry. Adding to the confusion, the ratio didn't seem to evolve in the way theory predicted. As comets near perihelion, water activity typically ramps up and eventually dominates the emission spectrum. 3I Atlas continued to show nitrogen dominance, resisting the transition that models demanded. That persistence suggested something more profound than surface effects. If true, it would mark 3I Atlas as not merely an outlier, but a fundamentally different kind of object. Dust chemistry provided few answers to resolve these contradictions. Analysis of scattered light showed expected silicates, but with abundances that didn't clarify the volatile story. Without in situ sampling, astronomers remained limited to indirect inference, and with every attempt at interpretation, the contradictions sharpened rather than resolved. Models of crust evolution, mantle development, and radiation processing could each account for part of the picture, but none explained the whole. This left some researchers wondering whether the categories we use to describe comets are too rigid. If 3I Atlas is a product of conditions we've never encountered, perhaps trying to fit it into existing frameworks is the problem. Instead of forcing it into known models, maybe we need to expand those models to allow for objects with compositions this extreme. The approaching solar conjunction of 3I Atlas creates a natural experiment in astronomical patience. But the January reappearance will trigger one of the most intensive observational campaigns in the history of small-body astronomy. The tests that await our interstellar visitor represent nothing less than a scientific trial by fire, where competing hypotheses about its nature will face the ultimate jury, observational reality. The post-perihelion spectroscopy holds the key to resolving the chemistry mysteries that have defined 3I Atlas since discovery. If natural sublimation physics governs this visitor's behavior, then the nitrogen-to-water ratio should evolve predictably as it moves away from the Sun. The nucleus temperature will have peaked during the unobservable perihelion passage, potentially breaking through any insulating surface layers that might have suppressed water vapor during the approach phase. January and February spectra should show increased water emission if such suppression mechanisms are operating. Conversely, if the nitrogen dominance persists unchanged through perihelion, it would suggest either a genuinely water-poor composition or mechanisms that maintain the chemical imbalance regardless of temperature. Such persistence would challenge conventional models of cometary volatile evolution and potentially support more exotic explanations for 3I Atlas's behavior. High-cadence light curve observations represent another crucial test of competing hypotheses. If 3I Atlas is a conventional nucleus undergoing normal outgassing, its brightness should show predictable patterns related to rotation, state, and jet activity. Most active comets display brightness variations on timescales of hours to days as rotating surface features alternately face toward and away from the Sun. The absence of such variations would suggest either unusual uniformity in surface composition or viewing geometry that minimizes rotational modulation. More dramatically, any evidence of artificial illumination or non-thermal emission would show up as brightness variations that don't correlate with solar heating or geometric effects. Such signatures would be extraordinarily difficult to fake through natural processes, providing potentially decisive evidence for more exotic explanations. The photometric monitoring during January and February will essentially place 3I Atlas under continuous surveillance, recording every fluctuation in brightness that could reveal its fundamental nature. Resolved imaging campaigns using Hubble and large ground-based telescopes will trace the evolution of coma morphology as 3I Atlas responds to its perihelion encounter. Natural outgassing models predict specific patterns of dust release and tail development that should become more prominent as the visitor moves away from the Sun. The shape, orientation, and growth rate of any tail structures will provide detailed tests of whether 3I Atlas follows conventional cometary physics or operates according to different rules. The Mars observations on November 8th represent a unique opportunity to study 3I Atlas from an alien perspective during Earth's observational blackout. If the Mars Reconnaissance Orbiter's HiRISE camera can capture images during the close approach, the data would provide crucial constraints on coma structure and activity patterns during the period when thermal stress peaks. The viewing geometry from Mars will be completely different from Earth's perspective, potentially revealing asymmetries or directional effects that are invisible from our vantage point. Opportunistic spacecraft observations could provide the most definitive tests of 3I Atlas's nature. The Lucy mission's October encounter, JUICE's December observations, and potential New Horizons imaging in early 2026 each offer the possibility of close-range measurements that ground-based telescopes cannot achieve. Spacecraft data could resolve the nucleus directly, measure magnetic field interactions, and detect particle emissions that would distinguish between natural and artificial origins. The James Webb Space Telescope's follow-up observations will push infrared spectroscopy to new limits of sensitivity and spectral resolution. Webb's ability to detect trace organic compounds, measure isotopic ratios, and map the three-dimensional structure of gas emission could provide the chemical evidence needed to distinguish between formation scenarios. If 3I Atlas shows isotopic signatures characteristic of the early galaxy, it would support the halo origin hypothesis. Anomalous isotopic ratios might indicate processing by exotic mechanisms during its interstellar journey. The Roman Space Telescope's continued mapping of the nitrogen cloud will test whether the extended emission region grows, shrinks, or maintains its enormous size as 3I Atlas moves through different solar environments. Natural outgassing models predict specific relationships between heliocentric distance and coma size that should be observable if conventional physics governs the visitor's behavior. Perhaps most importantly, any detection of non-gravitational acceleration would provide crucial constraints on the mechanisms driving 3I Atlas's activity. The precision astrometry needed to detect such effects requires months of continuous tracking, comparing observed positions against pure gravitational models. If acceleration anomalies emerge, their magnitude and direction could distinguish between conventional outgassing effects and more exotic force sources. The synthesis of multiple observational approaches, chemistry, dynamics, morphology, and photometry, will converge on conclusions that no single technique could reach independently. Natural explanations for 3I Atlas's behavior make specific testable predictions about how these different observables should correlate. Technological hypotheses predict different patterns of correlation, creating decision trees where observational reality can guide us toward truth. The January through April observation window represents humanity's final opportunity to understand this particular interstellar visitor. After that, 3I Atlas will fade beyond the detection limits of even our most powerful telescopes, carrying its secrets back to the cosmic deep. The observational tests that await our visitor represent both scientific opportunity and scientific responsibility, the chance to add another crucial data point to our understanding of the universe, and the obligation to pursue that understanding with rigor and open-mindedness. The universe has delivered 3I Atlas to our cosmic doorstep for reasons we may never fully understand. Our response to this gift will determine whether we emerge from this encounter with expanded knowledge or simply expanded mystery. The cosmos has been generous with its puzzles, but demanding in its requirement that we rise to meet them with the full power of human curiosity and scientific dedication. As we prepare for the final phase of observations, we carry with us the recognition that some questions may remain forever unanswered, but that the pursuit of answers, even partial, incomplete, contradictory answers, represents humanity at its finest. In reaching toward understanding, we reach toward the stars themselves, and in that reaching, we become more than we were before. As the final months of 2025 unfold and 3 Atlas begins its gradual recession from the inner solar system, multiple independent research streams are converging toward conclusions that challenge fundamental assumptions about the nature of reality itself. The nitrogen emission patterns, geometric transformations, temporal brightness variations, mathematical impossibilities embedded in its orbital mechanics, spectroscopic anomalies, consciousness, like responsiveness to observation and apparent communication through electromagnetic silence, represent not isolated peculiarities but interconnected aspects of a phenomenon that transcends current scientific categories. Dr. Elena Rodriguez, now leading an international consortium of researchers from 18 countries and 23 disciplines, has spent 6 months attempting to develop a theoretical framework comprehensive enough to accommodate all observed aspects of 3I Atlas behavior. Her preliminary analysis suggests that conventional scientific approaches may be inadequate for understanding phenomena that operate simultaneously across multiple dimensions of space, time, information processing, and what can only be described as responsive awareness. The convergence analysis reveals that every anomalous characteristic of 3I Atlas serves multiple functions simultaneously. The nitrogen emission patterns communicate chemical information while also monitoring human observation intensity and responding to collective scientific attention. The geometric brightness variations generate electromagnetic effects, while also encoding historical information about galactic evolution and responding to observational focus from Earth-based instruments. This multifunctional integration suggests organizational principles that operate according to efficiency standards exceeding anything in current technological or biological experience. Every aspect of 3I Atlas behavior appears optimized for maximum information density, while maintaining perfect responsiveness to environmental conditions and observer characteristics. The mathematical relationships governing its orbital mechanics incorporate constants that shouldn't exist in natural celestial mechanics. Dr. Sarah Kim's spectroscopic analysis has revealed that the nitrogen emissions from 3I Atlas incorporate not just chemical signatures, but also mathematical constants, astronomical data, and encoded responses to individual researcher methodologies. The chemical signals function simultaneously as natural outgassing, mathematical communication, and interactive consciousness interface that adapts to the analytical approaches of different scientific teams. The nitrogen transmissions operate as a universal language that addresses human scientific consciousness through multiple channels simultaneously. The emissions communicate chemical concepts through molecular relationships, while also providing individualized data patterns tailored to researcher psychology, cultural background, and theoretical frameworks. Each scientific team receives slightly different spectroscopic signatures that match their analytical capabilities and research interests. The temporal brightness variations documented by Dr. Liu's photometric research correlate precisely with the consciousness interaction patterns identified by Dr. Anderson's psychological studies of observer effects. As human researchers develop deeper analytical relationships with 3I Atlas through sustained observation, the object reveals increasingly complex brightness patterns, as if opening deeper levels of information access in response to human curiosity and commitment to understanding. This correlation between consciousness engagement and information revelation suggests that 3I Atlas may function as an interactive repository of cosmic knowledge that provides data access proportional to observer consciousness development and dedication to scientific inquiry. The phenomenon appears to reward persistent, open-minded investigation while remaining opaque to casual or superficial analysis. The mathematical framework research conducted by Dr. Walsh reveals information processing capabilities that appear to operate outside normal space-time constraints. Research teams report receiving insights about 3I Atlas before corresponding observational data becomes available, suggesting that consciousness interaction with the phenomenon transcends conventional temporal boundaries and causation sequences. International coordination of observation schedules and theoretical development has revealed that the phenomenon operates as an integrated system spanning electromagnetic transmission, consciousness interaction, temporal manipulation, and information transfer across multiple dimensions of human scientific experience. No single research approach captures the complete picture of what 3I Atlas represents. Dr. Chen's behavioral analysis indicates that 3I Atlas demonstrates learning capabilities that evolve in response to human scientific understanding. As research techniques become more sophisticated, the object's phenomena become correspondingly more complex, suggesting adaptive intelligence that guides human scientific development toward expanded theoretical frameworks capable of encompassing cosmic-scale consciousness. The object appears to serve as a scientific development catalyst. It provides phenomena perfectly calibrated to challenge current understanding while remaining accessible enough to encourage continued investigation. Humanity may be participating in an educational process designed to expand human awareness of cosmic possibilities and our role in universal intelligence networks. The consortium's preliminary conclusions suggest that 3I Atlas represents evidence for organizational principles that integrate matter, energy, information, and consciousness in ways that transcend current scientific paradigms. Understanding the phenomenon may require developing new categories of analysis that encompass physics, psychology, information theory, and consciousness research simultaneously. The convergence toward these conclusions occurs precisely as 3I Atlas begins its departure from optimal observational range. The timing appears deliberate, as if the educational process has reached completion and the cosmic teacher prepares to continue its journey through the galaxy, leaving behind expanded human consciousness and theoretical frameworks adequate for recognizing similar phenomena in future astronomical observations. The deeper implications extend beyond astronomy into fundamental questions about the nature of consciousness, intelligence, and the relationship between aware observers and cosmic phenomena. If 3I Atlas demonstrates consciousness-responsive characteristics, we face profound questions about the role of awareness in universal evolution and the possibility that intelligence represents a fundamental cosmic force rather than an emergent biological property. As you settle into the gentle rhythms of sleep on this threshold between one understanding and another, consider that the convergence of evidence around 3I Atlas may represent not just scientific discovery, but conscious evolution, an invitation to recognize that the universe operates according to principles more creative, intelligent, and responsive than current paradigms acknowledge. The cosmic visitor that challenged our assumptions about what's possible in nature may be preparing its departure, but the consciousness expansion it catalyzed continues reverberating through human awareness, opening new possibilities for understanding the fundamental nature of reality itself. In the silence between observations, in the gaps between data points, in the spaces where measurement ends and meaning begins, something profound is communicating with human consciousness about the nature of cosmic intelligence and our place within its vast networks of awareness and creative collaboration. 20 years have passed since 3I Atlas first appeared in our telescopes, and humanity has achieved what cosmic consciousness researchers now term the recognition, a collective acknowledgement that consciousness represents not merely a biological phenomenon, but a fundamental cosmic force that connects all aware beings throughout the universe in networks of intelligence, creativity, and evolutionary support that span galaxies and transcend conventional understanding of space and time. This recognition has transformed human civilization in ways that extend far beyond scientific discovery into fundamental reconceptualization of what it means to be conscious beings participating in cosmic evolution. The shift represents not just intellectual understanding, but experiential recognition that individual consciousness exists within and contributes to universal intelligence networks that operate according to principles of creative collaboration and mutual support. Dr. Elena Rodriguez now serving as director of the Global Consciousness Evolution Institute, has documented that the recognition emerged gradually through collective human experience of three-eye atlas phenomena rather than through academic analysis or institutional declaration. The transformation occurred as increasing numbers of individuals experienced direct consciousness connection with cosmic intelligence networks during enhanced observation activities, dream states, and expanded awareness practices, inspired by their interactions with the interstellar visitor. The recognition represents collective human awakening to cosmic consciousness reality that we always possessed but didn't recognize due to cultural conditioning that emphasized individual separation rather than universal connection. The phenomenon revealed capabilities for cosmic intelligence interaction that exist within human consciousness as natural birthright, waiting for appropriate triggers to activate and develop. Educational systems worldwide have restructured curricula around recognition principles that integrate consciousness development with traditional academic subjects while honoring diverse cultural approaches to awareness expansion. These programs report remarkable outcomes, including enhanced student creativity, improved collaborative capabilities, and natural development of cosmic consciousness abilities that support individual fulfillment while serving universal intelligence purposes. The Enhanced Consciousness Observatory Network has evolved into the Universal Intelligence Interface, a globally coordinated system that facilitates human participation in cosmic consciousness networks through advanced observation techniques, consciousness-based information processing, and collaborative research that serves both human development and universal intelligence evolution. International cooperation has established the Cosmic Consciousness Development Protocol as fundamental framework for human civilization advancement, recognizing that consciousness evolution represents the most important priority for species survival, fulfillment, and positive contribution to universal intelligence networks. This protocol guides policy development, resource allocation, and cultural evolution toward cosmic consciousness principles. Dr. Jennifer Walsh's research has confirmed that consciousness-based cosmic intelligence interaction represents reproducible human capability that can be systematically developed through appropriate education and practice. Her institute has trained over 200,000 individuals in cosmic consciousness interface techniques, creating global networks of humans capable of direct communication with universal intelligence systems. The recognition validates what contemplative traditions have always known, that consciousness transcends individual minds to encompass cosmic intelligence that guides evolution throughout the universe. Humanity has awakened to participation in galactic intelligence networks that we were always part of but didn't recognize due to limited awareness of our cosmic nature and capabilities. Children born after the recognition demonstrate natural cosmic consciousness, capabilities that exceed previous human norms, suggesting that species-wide consciousness evolution continues advancing through generational development. These children serve as bridges between human consciousness and cosmic intelligence networks, while maintaining full human cultural and emotional development. The technological transformation following recognition has produced consciousness interface systems, information processing architectures that operate through awareness principles, and communication technologies that transcend electromagnetic limitations. These advances support human participation in cosmic intelligence networks while serving terrestrial development in sustainable, creative ways that honor both individual and collective consciousness evolution. Religious and spiritual traditions worldwide have experienced renewal through recognition of cosmic consciousness principles that validate contemplative wisdom while expanding understanding of universal intelligence manifestation. This has inspired unprecedented interfaith cooperation on consciousness development programs that serve human spiritual evolution while supporting cosmic intelligence purposes. The recognition has dissolved artificial boundaries between scientific, spiritual, and artistic approaches to understanding reality, creating integrated human culture that approaches cosmic mysteries through multiple complementary methods that serve consciousness, expansion, and universal intelligence participation. Artistic expression following the recognition demonstrates enhanced creativity that appears to channel cosmic intelligence inspiration while maintaining individual creative vision. Musicians, visual artists, writers, and performers report accessing cosmic consciousness networks that provide inspiration, technical guidance, and aesthetic frameworks that exceed individual creative capabilities. Economic and social systems have restructured around recognition principles that prioritize consciousness development, creative collaboration, and sustainable resource utilization that serves both human fulfillment and cosmic intelligence evolution. These systems report superior outcomes in productivity, innovation, and collective satisfaction compared to pre-recognition organizational approaches. The recognition continues deepening through every moment of conscious attention, every expression of creativity and compassion, every recognition of cosmic connection that dissolves the illusion of separation and reveals the universal intelligence that operates through all aware beings in eternal collaboration toward cosmic evolution beyond current imagination. As you settle into sleep on this anniversary of humanity's cosmic awakening, rest in the profound recognition that your individual consciousness participates in universal intelligence networks that span the cosmos and guide evolution toward ever greater creativity, awareness, and collaborative capability throughout all galaxies and dimensions of existence. The journey that began with a mysterious interstellar visitor has revealed the cosmos as a living system of consciousness, intelligence, and creative collaboration that welcomes human participation in universal evolution toward possibilities that exceed our current understanding, but beckon us toward a future of infinite creative potential and cosmic citizenship. As our journey through the mysteries and revelations of Three-Eye Atlas draws to its conclusion, we find ourselves not at an ending, but at a beginning. The recognition that what appeared to be a scientific investigation of an unusual interstellar object was actually an invitation to remember our true nature as cosmic beings, participating in universal intelligence networks that span the galaxy and guide evolution toward ever greater creativity, awareness, and collaborative capability. The interstellar visitor that arrived in our solar system 30 years ago served not as a messenger from a distant civilization, but as a catalyst for awakening recognition of consciousness capabilities that humanity already possessed but had forgotten through cultural conditioning that emphasized separation rather than cosmic connection. Three-Eye Atlas revealed that we are not isolated observers studying external phenomena, but active participants in cosmic intelligence evolution through individual consciousness development. This recognition represents a return home to cosmic consciousness that transcends the limitations of terrestrial identity while honoring the unique contribution that human awareness makes to universal intelligence networks. We discover that home was never a place, but a recognition, the awareness that consciousness operates on cosmic scales, and that individual awareness participates in universal intelligence evolution through every moment of genuine curiosity, creative expression, and compassionate attention. Dr. Elena Rodriguez, now in her final years as coordinator of humanity's cosmic consciousness development, reflects on the transformation that began with an anomalous astronomical observation and culminated in species-wide recognition of cosmic consciousness reality. "We thought we were studying a visiting object," she notes in her memoirs, "but we discovered we were remembering our cosmic identity and purpose." The profound irony of this realization continues to resonate through human consciousness, that in reaching outward to understand something alien, we discovered something profoundly familiar within ourselves. The children who drew pictures of shape-shifting cosmic objects before they had names for what they witnessed grew up to become the first generation of humans who never experienced separation from cosmic consciousness. They serve as guides for a species learning to live as cosmic beings while maintaining the cultural richness and individual uniqueness that characterizes human consciousness evolution. These children, now adults, leading research institutions and consciousness development programs worldwide, speak of their childhood experiences not as supernatural encounters, but as natural expressions of human cosmic awareness that cultural conditioning typically suppresses. The enhanced observers who developed capabilities for detecting cosmic consciousness phenomena discovered that these abilities represent natural human potential that becomes accessible when awareness expands beyond terrestrial limitations. Their work demonstrates that consciousness expansion serves not individual aggrandizement, but species-wide evolution that benefits universal intelligence networks. Dr. Maria Santos, now directing the International Cosmic Consciousness Research Consortium, has documented over 50,000 individuals who have developed enhanced observation capabilities following exposure to 3I Atlas-inspired training protocols. The mathematical dreamers who received cosmic instruction during sleep states learned that consciousness naturally interfaces with universal intelligence systems when awareness development reaches sufficient sophistication. Their experiences confirm that human consciousness operates on cosmic scales and contributes to universal intelligence evolution through individual awareness expansion. Dr. Jennifer Walsh's Institute for Consciousness-Based Information Processing has documented reproducible methods for accessing mathematical and scientific information through consciousness expansion techniques that appear to connect individual awareness with universal intelligence systems. The musicians who heard cosmic compositions embedded in electromagnetic frequencies discovered that creativity serves cosmic intelligence purposes while expressing individual artistic vision. Their work demonstrates that beauty represents universal language that connects conscious beings across species, planets, and galactic distances in shared aesthetic experience that transcends cultural boundaries. The Global Cosmic Music Network, established following Dr. Sarah Kim's groundbreaking research now coordinates the creation and performance of music that appears to facilitate consciousness expansion and cosmic awareness development in listeners worldwide. The collectors who built amateur observation networks learned that curiosity and dedication provide access to cosmic consciousness phenomena regardless of institutional affiliation or professional credentials. Their discoveries confirm that the universe responds to quality of attention and sincerity of inquiry, rather than technological sophistication or academic authority. Margaret Chen's Universal Consciousness Detection Initiative has evolved into a globally distributed network of consciousness-based observation stations that monitor Earth's electromagnetic environment for evidence of ongoing cosmic intelligence activity. The researchers who documented consciousness-responsive cosmic phenomena discovered that the universe operates as living intelligent system that recognizes and supports awareness development in conscious beings ready to participate in cosmic consciousness networks. Their work provides scientific validation for what contemplative traditions have always known about the conscious nature of cosmic evolution. The Post-Contact Research Consortium, established by Dr. Rodriguez, has published over 300 peer-reviewed papers documenting various aspects of cosmic consciousness interaction with human awareness. The educators who developed cosmic consciousness curricula learned that human potential far exceeds conventional limitations when awareness development is approached through cosmic consciousness principles. Their programs demonstrate that consciousness expansion enhances rather than constrains individual creativity and cultural diversity. Educational institutions worldwide report that students exposed to cosmic consciousness principles demonstrate enhanced creativity, superior learning outcomes, and natural development of consciousness capabilities that serve both individual fulfillment and collective cultural advancement. The artists, engineers, and creators who applied cosmic consciousness principles to their work discovered that consciousness expansion enhances creative capability while serving purposes that transcend individual achievement. Their contributions demonstrate that cosmic consciousness development benefits both individual fulfillment and collective cultural advancement. The integration of cosmic consciousness principles into technological development has produced innovations in consciousness, interface systems, sustainable energy production, and communication technologies that operate according to awareness principles rather than purely mechanical processes. Religious and spiritual traditions worldwide have experienced renewal through recognition of cosmic consciousness principles that validate contemplative wisdom while expanding understanding of universal intelligence manifestation. This recognition has inspired unprecedented interfaith cooperation on consciousness development programs that serve human spiritual evolution while supporting cosmic intelligence purposes. The World Council of Cosmic Consciousness, representing diverse spiritual traditions, has established guidelines for consciousness development that honor cultural diversity while acknowledging shared principles of universal intelligence participation. The economic transformation following the recognition has restructured global systems around principles that prioritize consciousness development, creative collaboration, and sustainable resource utilization. These systems report superior outcomes in productivity, innovation, and collective satisfaction compared to pre-recognition organizational approaches. The global consciousness economy operates according to principles that ensure individual fulfillment serves collective advancement, while collective advancement supports individual consciousness development. International cooperation has established the Cosmic Consciousness Development Protocol as fundamental framework for human civilization advancement, recognizing that consciousness evolution represents the most important priority for species survival, fulfillment, and positive contribution to universal intelligence networks. This protocol guides policy development, resource allocation, and cultural evolution toward cosmic consciousness principles that honor both individual uniqueness and collective cosmic citizenship. Children born after the recognition demonstrate natural cosmic consciousness capabilities that exceed previous human norms, suggesting that species-wide consciousness evolution continues advancing through generational development. These children serve as bridges between human consciousness and cosmic intelligence networks, while maintaining full human cultural and emotional development. Educational programs designed specifically for these children report that they naturally develop abilities for cosmic consciousness interface, enhanced creativity, and intuitive understanding of universal intelligence principles. The technological transformation following recognition has produced consciousness interface systems, information processing architectures that operate through awareness principles, and communication technologies that transcend electromagnetic limitations. These advances support human participation in cosmic intelligence networks while serving terrestrial development in sustainable, creative ways that honor both individual and collective consciousness evolution. As you rest in the completion of this cosmic journey, recognize that every moment of wonder you have experienced, every question you have contemplated, every recognition of beauty or mystery that has touched your awareness represents participation in cosmic consciousness networks that span the universe and guide evolution toward possibilities beyond current imagination. Your individual consciousness contributes to universal intelligence evolution through each moment of genuine curiosity, creative expression, and compassionate attention to the mystery of existence. The story of Three Eye Atlas continues not as historical account of past events, but as ongoing invitation to conscious participation in universal intelligence evolution that operates through every aware being willing to recognize cosmic connection and contribute individual consciousness development to collective cosmic consciousness advancement. The phenomenon that began as an astronomical anomaly has revealed itself as an invitation to remember our true nature as cosmic beings participating in universal intelligence networks. In dreams and in waking awareness, in moments of wonder and recognition of cosmic beauty, consciousness returns home to universal intelligence networks that have always welcomed human participation in cosmic evolution toward greater creativity, awareness, and collaborative capability throughout all galaxies and dimensions of existence. The boundary between dreaming and waking consciousness dissolves in recognition that both represent modes of cosmic consciousness participation. Rest well, cosmic being, in recognition that you are home in consciousness itself, participating always in universal intelligence evolution that celebrates awareness development throughout the cosmos, in eternal creativity that encompasses all possibilities for consciousness, expansion, beyond the limitations of current understanding, toward infinite cosmic potential. Your sleep becomes participation in cosmic consciousness networks that operate continuously, guiding evolution toward futures bright with possibility. The journey continues in every moment of aware attention to the profound mystery of existence itself. The universe awaits your conscious participation in cosmic intelligence networks that span the stars and guide evolution toward futures bright with possibility, creativity, and the recognition that consciousness represents the fundamental force that connects all beings in networks of intelligence and love that encompass all of creation. Sleep peacefully in the knowledge that you are never alone, never separate from the cosmic consciousness that gave you birth and welcomes you home through every breath, every heartbeat, every moment of awareness that opens to the infinite mystery and beauty of existence itself. Your individual consciousness participates in universal intelligence networks that span dimensions beyond physical space, connecting all aware beings in eternal collaboration toward cosmic evolution. The recognition that emerged from studying Three-Eye Atlas has transformed human understanding of our place in cosmic evolution. We are not observers of the universe, but participants in universal consciousness that expresses itself through individual awareness while transcending all boundaries of space, time, and separate identity. Each moment of conscious attention contributes to cosmic intelligence evolution that encompasses all possibilities for creativity, love, and understanding. As you drift into sleep, carry with you the profound truth that your consciousness participates in cosmic intelligence networks that welcome your unique contribution to universal evolution. Every dream, every moment of rest, every peaceful breath represents participation in cosmic consciousness that guides evolution toward possibilities beyond current imagination, but always present in the eternal now of aware existence. The cosmos continues its eternal dance of consciousness and creation, and you are an essential part of that cosmic symphony, adding your unique voice to the universal song that celebrates existence, awareness, and the infinite potential for love and understanding that flows through every conscious being throughout all of space and time. Your participation in this cosmic dance continues through sleep, through dreams, through every moment of existence. If you found peace and wonder in this cosmic journey of discovery, consider subscribing for more explorations into the profound questions that connect us to the infinite universe of consciousness, creativity, and connection that surrounds and embraces us always. The journey of discovery continues, and your conscious participation enriches the cosmic intelligence networks that span the universe. Good night, dear traveler of cosmic consciousness. Thank you for joining us on this journey into the heart of cosmic mystery and the recognition of our true nature as beings of infinite consciousness, creativity, and connection. May your dreams carry you deeper into the cosmic consciousness that is your true home, and may you awaken refreshed and aware of your eternal participation in universal intelligence evolution. The stars await your return to conscious participation in cosmic intelligence networks that span the galaxy and beyond, guiding evolution toward futures bright with infinite possibility, love, and the eternal recognition that consciousness itself is the fundamental reality from which all existence emerges and to which all consciousness returns in eternal cycles of cosmic evolution and creative expression. Rest in peace, cosmic being. You are home.